Hello and welcome to all students. In this lecture we learn about convergence and divergence of series. So first of all we have seen in the previous lecture introduction to the series, geometric series, and in this lecture we learn about convergence and divergence of a series. Third point. And in successive lectures we will see the next points. So algebra of convergent series. Algebra of convergent series. So whenever we have two convergent series, we can add them or subtract them term by term or multiply them by constant to get a new convergent series. We get formal statement of result as follows. So this is the algebra of this theorem is related to the algebra of convergent series, algebra of series. If summation an and summation bn are convergent series, then so are the series summation an plus bn, summation an minus bn, and summation can, where c is a constant. And summation an plus bn is equal to summation an plus summation bn, means series an plus bn is equal to series an plus series bn. So this is addition of two series. Summation series an minus bn is same as series an minus series bn, and series c into an is equal to c into series an. So let us write the proof of all these three statements. Proof: the results for series follows from the analogous result of sequences. Let Sn is equal to a1 plus a2 plus plus an be a sequence of partial sums of series summation an, and let Tn is equal to b1 plus b2 plus plus bn be a sequence of partial sums of series summation bn. And suppose series an converges to S, means series an is equal to S, and series bn converges to T, means series bn is equal to T. Now let the nth partial sum for series ak plus bk be un, and it is equal to summation ai plus bi, I runs from 1 to n. Therefore un can be written as un equal to summation ai plus bi. So we can write all the terms of this series. So first term is a1 plus b1 plus second term is b2 plus a2 plus b2 plus plus nth term is an plus bn. Now we remove all these brackets and we take together terms of ai and take together terms of bi. So in first bracket a1 plus a2 plus plus an, and plus in the second bracket b1 plus b2 plus plus bn. So first bracket is nothing but sequence of partial sum Sn, and second term is nothing but sequence of partial sum Tn. So un is addition of these two sequences, sequence Sn and sequence Tn. So un is addition of two sequences of partial sums, sequence Sn and sequence Tn. And let us take the limit of this un as n tends to infinity, and it is equal to limit n tends to infinity, but un is nothing but Sn plus Tn. So we write limit n tends to infinity of Sn plus Tn. and it is equal to limit Sn n tends to infinity plus limit Tn n tends to infinity. It is equal to S plus T. This shows that the limit of sequence of partial sums Sn plus Tn is S plus T. This shows that the limit of sequence of partial sum Sn plus Tn is S plus T. Okay. Therefore, the series that is the sequence of partial sums, sequence Sn plus Tn is convergent and converges to S plus T. This implies that the series summation an plus bn as n tends n equal to 1 to infinity converges and converges to S plus T. That is summation an plus bn is equal to S plus T. Therefore, the given series is convergent and converges to S plus T. Or what we have is finally, therefore summation an plus bn is equal to S is nothing but summation an and T is nothing but summation bn. Therefore, series an plus bn is equal to series an plus series bn. The proof of difference of series is similar to that of proof of addition of series. A student should try writing down it. So series an minus bn is equal to series an minus series bn. Now we prove the result of constant multiplication of the series. Let say sequence Vn be a sequence of partial sum of series Can. Therefore, Vn is equal to C into A1 plus C into A2 plus dot 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 plus C into An. Therefore, Vn is equal to, on the right hand side we take C common, C into bracket A1 plus A2 plus dot 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 plus An. This implies that Vn is equal to this bracket, C into bracket is nothing but Sn. So Vn is equal to Csn. Therefore, limit Vn n tends to infinity is equal to limit Csn equal to C, take outside C, limit Sn n tends to infinity. C into limit Sn n tends to infinity. So limit Sn n tends to infinity is nothing but S. Therefore, limit of Vn n tends to infinity is equal to Cs. This shows that the sequence of partial sum Vn of series Can converges to Cs, and therefore the series Can converges to Can. C into S, but S is nothing but series An. Okay. Now let us write some remarks. Every non-zero constant multiple of a divergent series is divergent. Every non-zero constant multiple of a divergent series is divergent. Means if we have a divergent series and if we multiply by a non-zero constant to that series, then the resultant series is also divergent. If the series n runs from 1 to infinity converges and series Bn diverges, then the addition of these two series An plus Bn n runs from 1 to infinity and series An minus Bn n runs from 1 to infinity both diverges. So in addition of two series and in subtraction of two series, if one series is convergent and other series is divergent, then the addition of series or that subtraction of series is also divergent. So if at least one of these two series is divergent, then the addition of series and the subtraction of series is also divergent. However, the divergence of both the series An and series Bn, does not guarantee that does not guarantee that the divergence of series, addition of series and subtraction of series. So see once again, however, the divergence of both the series an and series bn, does not guarantee that divergence of addition or subtraction of series. So let us take one counter example. Let us consider a series an equal to 1 minus 1 plus 1 minus 1 plus 1 minus dot dot dot, and consider the another series bn equal to minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot dot dot. So if we take the addition of these two series, be two divergent series. So that is important. These two series are divergent. We know that, or we can show it is divergent. Okay. Why these two series are divergent? Because the sequence of partial sums of these two series are divergent. Sequence of partial sums of these two series are divergent. Therefore, these two series are divergent. Okay. Here an plus or minus bn is equal to 0 for all n belongs to n. If we take the addition of nth terms an plus bn plus or minus bn, then what happens here? This addition or subtraction is 0 for all n belongs to n. Therefore, this addition or subtraction series is a 0 series and it converges to 0. Okay, converges to 0. This shows that the series an plus or minus bn is convergent even though both the original series an and series bn are divergent. Let us take one example. Find the sum of the series 5 upon n into bracket n plus 1 plus 1 upon 2 raised to n. Solution from algebra of series. Given series can be written as, from algebra of series, given series can be written as, see here, just we are simplifying the given series. Series 5 upon n into bracket n plus 1 plus 1 upon 2 raised to n is equal to, we are separating these two series. Okay, so 5 is a constant, take outside, series n runs from 1 to infinity, 1 upon n into bracket n plus 5 n plus 1 plus series 1 upon 2 raised to n. So let us call it is statement 1. Here first we consider series summation 1 upon 2 raised to n. But what is the type of this series 1 upon 2 raised to n? Series 1 upon 2 raised to n. This series is geometric series with first term a is equal to 1 half. And what is the common ratio? And the common ratio is r equal to 1 half. And we observe that modulus of r is equal to 1 half and it is strictly less than 1. Therefore, by the result of geometric series, this implies that the series summation 1 upon 2 raised to n is convergent and converges to a upon 1 minus r, and it is equal to 1 half divided by 1 minus half, and finally what we get is 1. Therefore, series 1 upon 2 raised to n is converges to 1. Okay, that is important. Now consider the series. Now consider the series summation 1 upon n into bracket n plus 1, and we check the convergence of this series. Let Sn be a sequence of partial sum of the above series. Let Sn equal to summation 1 upon k into bracket k plus 1, k runs from 1 to n. So this Sn contains n terms. So this is sequence of partial sum of the above series. Be a sequence of partial sums, and Sn is equal to, just we simplify this function by using the partial fraction 1 upon k minus 1 upon k plus 1. So how to do this? You can check it. 1 upon k into bracket k plus 1 can be written in this format: 1 upon k minus 1 upon k plus 1. So Sn is like this. Now we write all the n terms of this Sn. Sn is equal to first term is 1 minus 1 half plus second term is 1 half minus 1 by 3 plus third term is 1 by 3 minus 1 by 4 plus dot 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 plus 1 upon n minus 1 upon n plus 1. So I have written all the n terms of this Sn, but we observe that from the first bracket minus 1 half will get cancelled with 1 half in the second bracket. Again minus 1 by 3 from the second bracket will get cancelled with plus 1 by 3 in the third bracket. So in this way almost all terms will get cancelled, and what is left is 1 minus 1 upon n plus 1. These two terms will be left. So Sn is equal to 1 minus 1 upon n plus 1, and we take a limit of this Sn. Limit Sn n tends to infinity is equal to limit n tends to infinity into bracket 1 minus 1 upon n plus 1. As n tends to infinity, what we get, so limit of 1 is 1 and limit of 1 upon n plus 1 is 0. So what we get is finally it is 1. So limit of Sn is equal to 1. Okay, so finally we can say that the sequence of partial sum Sn converges to 1, that is the series 1 upon n into bracket n plus 1 converges to 1. Series 1 upon n into bracket n plus 1 converges to 1. Now both the series, now equation 1 becomes, this shows that series 1 upon n bracket n plus 1 is equal to 1. Now from equation 1 what we have, so this first line is equation 1. So for you as it is, and write the values of these two series, summation 1 upon n into bracket n plus 1 and summation 1 upon 2 raised to n. So 5 into 1 plus 1, so it is 6. Therefore the given series converges to 6, convergent and converges to 6. Finally given series is convergent and converges to 1, no, converges to 6, okay, not 1. So finally given series is convergent and converges to 6 and not 1. Okay, so let us stop here, and this is the end of our lecture. Thank you very much.